Morning, everyone. Mr. Boothman here. It is the end of our week, so I'm going to go ahead and do College Friday on Thursday. How exciting. I guess this week I just want to address school pride. So, a lot of you give me a hard time about always bringing up Northwestern and having Northwestern hanging everywhere. Honestly, I think all of you bring it up a lot more than I do, but anyway. I think it's important to have some pride in an organization you're a part of, okay? If it's a worthwhile organization, if it's something that you agree with and you stand by. And for me, Northwestern is that. It's a fantastic school. I'm really proud to have gone there. But, that's not to say that other schools aren't. A lot of you, I hope, jokingly ask, do you think you're better because you went to Northwestern? Absolutely not. I don't care if you went to ASU or Harvard or GCU or Stanford. You went to college. You have a degree. You completed a course of study, and that's a huge accomplishment. So wherever you end up, just keep that in mind. Few things bother me more than someone who's incredibly pretentious and condescending based on where they went to school. We all went to school, okay? And almost any college you attend, everyone there is going to be pretty smart, okay? So how are you going to distinguish yourself from that? That's really the key, and that's what's going to set you up for success later on in your life and even starting now. So take some pride in wherever you choose to go to school, and let's move on to our lesson. Good morning. Hopefully your Unit 8 exam went well, okay? We're starting our very last unit of the year today. I personally am very sad about this. I absolutely love pre-calc. I love teaching it, but I'm also incredibly excited because our very last unit this year really puts the calculus in pre-calculus. We've looked at functions, we've looked at a bunch of different types of functions: polynomials, rationals, exponentials, logs, trig, analytic trig. We looked at vectors, and then we looked at sequences and series, another way of examining functions through a different lens. Unit 9, we're going to spend the last few weeks here on Unit 9 before we turn to a bit of review and some work time on your culminating activity, is limits and continuity. Okay, limits and continuity. This is also the very first unit of AP Calculus and any standard calculus course in college. So you're really beginning calculus right now. Very exciting. Before we jump in, okay, just a couple of notes. First, when I say Unit 9, really this unit is a single section. Okay, juniors, we're going to look at the second section in this unit, 9.2, continuity, during our last week together, but that's going to be after the seniors are done and after you submit your culminating activity. So by Unit 9, I really only mean this single section. We're only looking at limits here. That's all that will be assessed. And then juniors, we'll look at the idea of continuity and what that means and how it relates to limits during our last week together. Okay, and really prep you for AP Calc next year. You'll have an exit ticket due by midnight tonight. This, of course, is counting toward that attendance. You need to complete at least 50% of these exit tickets since April 6th through the end of the year in order to receive credit for this quarter. Okay. Let's jump right in. Section 9.1, limits. What is a limit? Okay, it's this very advanced sounding thing. It sounds very complicated, but a limit is actually a pretty straightforward concept. Okay, it's the value a function output approaches as the function input approaches a specific value. Okay, so what does that mean? Just consider a graph. Okay, let's say we have a parabola. Okay, so on this parabola, we know we have the point 1, 1. As our x value approaches 1, okay, so as we approach x equals 1 on this graph, what is our output approaching? As x approaches 1, what is our y value approaching? It's also approaching 1. Okay. So that limit as this function, as this parabola, approaches x equals 1 is y equals 1. That's all that a limit is, okay? Graphically, that's the concept, okay? What output is our function approaching as we approach a specific input? We use some special notation for this, okay? And the notation we use looks fancy, but it's also a little easier than it seems, okay? So this is read as the limit as x approaches a of f of x. So I've told you time and time again, mathematicians, we like to be as succinct, as precise, as some might say lazy as possible. So instead of writing out the full word limit, we just write the first 3 letters, L-I-M. We have the limit as x, this arrow means approaches a, so a is just some value of x, of whatever function is here, of f of x. So, for example, we had this parabola, and we said the limit as we approach x equals 1 is y equals 1. So how would we express this limit using our notation? It's the limit as x approaches 1, in this case a is 1, of, what was our function here? It was a parabola, so just x squared. And what did we say this equals? What was the y value that we're approaching? 1. Okay? A key point here, okay, very important to remember. This idea of the limit, okay, depends on approaching this value, not just from this side of x equals 1, but also from the other side of x equals 1. So as we approach this x value from both sides, what y value are we getting closer and closer to? 1. Okay, so if we were approaching a different y value from one of our sides, we'll talk about what that means in a second. But for now, pause it if you need to. This is very new notation. This is literally, quite literally, calculus. Okay, so take a second. Make sure you understand what this is. Okay, the limit, it's very scary, it's very intimidating, but that's all it means. What y value are we approaching on our graph from both sides of an x value? So we're going to start, if you notice our learning target here, 9.1, I can evaluate limits numerically, graphically, and algebraically. Okay, we're going to start by looking at these limits graphically. So looking at a graph like this and literally seeing what y value we're approaching. And then we'll spend the next few weeks looking at numerically and algebraically. Okay, but let's start, and this is as far as we're going to go today, just this first example, okay, A, B, and C. Evaluate the following limits using graphs. Part A. The limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, so if we're evaluating these graphically, we need to graph whatever this function is. And then we're going to see what y value are we approaching as x approaches 1. So let's sketch the graph of this. What kind of function is x squared minus 1 over x minus 1? This is a good old rational function. So to graph a rational function, we first simplify the function. So we can factor the numerator. And now x minus 1 cancels, and what are we left with? X plus 1. What happens at this x value that we canceled out of our rational function? If we cancel, that ends up being a hole in our graph. So there is a hole at x equals 1. Okay, so those rules are coming back in a pretty big way. And looking at what we ended up with, this simplified function, is it top heavy, bottom heavy equal? Does it actually have a numerator denominator anymore? Okay, well, its denominator is 1, so it ended up just turning into a basic linear function. So there is no vertical asymptote and horizontal or slant asymptote. We don't have to worry about any of that. So this right here is really just reaching back to unit 2b, rational functions. And now we sketch the graph of this. So we have the line x plus 1. So we know y equals x is just the diagonal line. Plus 1 is shifts the whole thing up 1. Okay, so here is our graph. But we have this hole at x equals 1. So we go to our graph here at x equals 1. There's a hole there in our graph. Now let's actually answer this question. So we graphed our function. What is the limit as x approaches 1? So from both sides of this x value, from the left of x equals 1 and from the right of x equals 1, what y value are we approaching? So we're getting closer and closer to x equals 1 here. And what y value are we getting closer and closer to as we get closer to x equals 1? That's y equals 2. And are we approaching 2 from both sides of x equals 1? Yes. So this limit as x approaches 1 of this function is 2. That's all we have to do. The hard part here was graphing the function, but once we have the graph, very straightforward. We're just looking. And as we get closer to this x value, what y value are we approaching? Okay, so pause for a second. And now we'll continue. Let's look at part B. All right, this time we have the limit as x approaches 1 of, all right, if we recall, this is going all the way back to unit 1. This is a piecewise function. Piecewise function just means we have 2 pieces of the function. Okay. So we just graphed this top piece. So for all values of x, not including 1, this is our graph. And we just discovered what that graph looks like. It's just this line. But we're excluding x equals 1. So in other words, there ends up being like a hole there on this graph. And we have this second piece of the function. The function equals 1 when x equals 1. So when x equals 1, the function equals 1. So we have this point just sitting there. When x equals 1, there's our function. And when x doesn't equal 1, we're on this line, but there ends up being that hole there. Same concept. Now that we have this graphed, let's consider the limit. So on our graph, on our function, for x does not equal 1, so that means from both sides of 1, okay, what are we getting closer to? What are we approaching here? What y value are we approaching as we get closer to x equals 1? We're approaching the y value of 2 again. I know that the function itself equals 1, okay? That's somewhere else. But just looking at what we're approaching 2. So that is the key of what a limit is. That distinguishes a limit from just a function value, okay? What is the function approaching? We don't actually care about what the function equals at a specific point. We're more interested in what it is approaching, what it's getting closer to. And in this case, that's 2. We have one last part to this example, part C, and that's the limit as x approaches 1 of x plus 1. Okay, x plus 1, we've been graphing that a few times now. Here's our line. We don't have to exclude any values here. Okay, it's not like there was a hole, there's not a piecewise function, it's just this line. So as x approaches 1, what y value are we getting closer and closer to? Yet again, our limit is 2. So we have 3 very different functions, completely different functions. They're related, but they are different functions, yet their limits are all the same. Very interesting, this idea of the limit, this concept. It's very different from what we're used to. But that's all that this is saying. Just to wrap up what we just said, the key point here is that the graph must approach the same value from both sides. The graph must approach the same value from both sides. Must be from both sides. We call these specific types of limits two-sided limits, okay, for obvious reasons. From two sides, we're approaching the same value. Now, there's also this idea of a one-sided limit. So that's a value the function approaches just from the left or from the right of a specific x value. The very last thing I want to write down today is we do have some specific notation for that. So usually, this is the two-sided limit. The limit as x approaches a of f of x. And we take, we take this to mean that we're approaching this value from both sides. Okay. Now we also have this idea of a one-sided limit. This is the limit as x approaches a from the left of f of x, and the limit as x approaches a from the right of f of x. So this plus and this minus, they kind of go in the place of an exponent on a. And all this is saying, if there's a little minus there, that means we're approaching this value from the left. If there's a little plus there, we're approaching that value from the right. And then if there's no plus or minus, we take that to mean that we're approaching that value from both sides, from both the left and the right. So this is as x approaches a from the left, and this is as x approaches a from the right. Now, really, we're going to focus on two-sided limits here, but this notation for the one-sided limit becomes very important later on in calculus, and for juniors, we'll look at this notation once we talk about section 9.2, continuity. So that is what a limit is. That's all that a limit is. It's a function, or it's a value the function approaches as we approach a specific x value. We're going to spend a lot of time talking about the limit, and really just this one section 9.1. It's a very unique concept, especially compared to anything else that you've studied in math so far. Okay, I'm very excited to be starting this with you. Please reach out to me if you have any questions or concerns. Okay, you cannot fall behind now, or you will be lost for the next 3 weeks. You have that exit ticket due by midnight tonight, and I encourage you to start looking at the 9.1 independent practice. You might not be able to do a whole lot of it, but start thinking about this concept of this idea of sketching a graph and evaluating what y value we're approaching. Join our Google Meet with questions, and I'll see you on Monday. All right. Well, I hope you enjoyed your first look at limits for pre-calc and those lovely FRQs if you're in AP Calc. I will see you all on Monday. Please enjoy your weekend and have a good one.